And this is chapter 8, which is bonding. And you can see your table of contents. We'll talk about Lewis structures and things like that. The bonding, types of bonding we're going to talk about, whether it be ionic or covalent, are going to involve those electrons in the valence shell. So the attractive forces that hold atoms together in compounds is called a chemical bond. The A group elements tell us the number of valence electrons. 1A is 2, or 1A is 1, 2A is 2, 3A is 3, 4A is 4, 5A is 5, 6A is 6, 7A is 7, 8A is 8, except for helium, which only gets 2, because it only has 2 electrons. Chemical bonds are going to be divided in 2 basic types. Ionic bonding, which we've spent a lot of time focusing on, which refers to the transfer of electrons and then they stick together by electrostatic attraction. Covalent bonding results from the sharing of one or more electron pairs between the 2 atoms. That's going to be the type of bonding we'll focus on in this chapter. Lewis dot formulas are just essentially the symbol of the element surrounded by the number of dots, where the number of dots equals the number of valence electrons it has. Notice I kind of start on one side, work my way around, then go back and start pairing the dots up, with the exception of helium, which has 2 paired dots, which is supposed to be symbolic of the fact it's a noble gas and those electrons are paired and aren't involved in any kind of bonding. Well, there's a couple of different ways to draw it, and the way that makes this useful is that if that particular compound forms a covalent bond, then the number of unpaired dots in the Lewis dot structure, if you draw them this way, is equal to the number of bonds that that atom would typically form in a compound. Not always form in a compound, but typically form in a compound. Like hydrogen only tends to form 1 bond. Boron likes to form 3 bonds. Carbon likes to form 4, so on and so forth. And we can see elements in the same periodic group do have the same Lewis dot structures. That is, they have the same number of dots around the symbol of the element. So if we look at covalent bonding, covalent bonds are formed when atoms share electrons. If the atoms share 2 electrons, then that's a single bond. If the atoms share 4 electrons, it's a double bond. If they share 6 electrons, it's a triple bond, meaning that bonds are indicated by lines, and one bond is 1 line. A double bond would be 2 lines. A triple bond would be 3 lines. If it's atoms that belong only to that atom, we call those lone pairs, and those would be indicated as paired dots. And I'll show you how that works when we work some examples. Right. Lewis formulas, then the octet rule states that the representative elements attain a stable noble gas configuration, 8 electrons in most of their compounds. Hydrogen is a notable exception where it only gets 2 because there's no p electrons on the first row. And so a lot of times people will work that, even at a high school level, into the octet rule. Everything gets 8 except for hydrogen, which gets 2. But regardless, we'll talk about some compounds in this particular course where we will look at violations of the octet rule, but not right away. But we want to try to make everything obey the octet rule if we can. So here are the rules. Count the valence electrons. That'll be the total number of electrons available on the structure. If the molecule's charged, we're going to add or subtract electrons to account for that. Then we're going to draw a skeleton for the molecule. That is, every atom has to be attached to at least one other atom in the molecule with a single bond at least. Then you want to obey the octet rule. Try to add bonds or non-bonding pairs so that the number of electrons is 8 on everything except for hydrogen. And sometimes that's not possible. So what you do is you draw your skeleton, see how many electrons are needed to complete the structure. If I have enough non-bonding electrons to do that, just add your non-bonding electrons. If there aren't enough, then you're going to add double or triple bonds. But it's for double and triple bonds is for if you have too few electrons, not too many. And some people get that backwards and mess it up. and then put the remaining electrons around the central atom, even if there's more than an octet. We'll come back to that concept of violating the octet rule, and I'll show you some cases where that could happen. We're going to start by drawing Lewis structures for some diatomic elements so that we can get the rules down. Okay, so let's look at a few simple Lewis structures, see if we can get the rules in for the most part. So let's start with H2, and we'll do these in increasing order of difficulty. So we can see that we've got, for hydrogen, we've got 2 hydrogens in the molecule. Now, if I look, hydrogen's in group 1A, so that's 1 valence electron for a total of 2 electrons. We go to draw the skeleton. Hydrogen is going to be attached to hydrogen with at least a single bond, right? Now that's a single bond, just one line. If we take away 2 electrons from that, we're not going to have any left over. Let's see if our octet rule is satisfied. Everything should have 8, with the exception of hydrogen, which is important in our case, which would get 2. Now those bonded electrons tend to count for both hydrogens. So I'd say each hydrogen has 2 electrons in this case. So the octet rule is satisfied, and we're done with that one. Now, next one, we got 2 fluorines. Fluorine's in group 7A, so 7 valence electrons for a total of 14. Fluorine is going to be bonded to fluorine. So this time when I take away 2, I've got 12 left. So when I evaluate the octet rule, each fluorine is supposed to have 8, but they only really have 2. So I need 6 more. 6 times 2 is 12. So that means I would add in the non-bonding electrons. Non-bonding electrons, each dot represents an electron. Dots are paired as long as you got an even number of electrons. If you don't, that's something called a free radical. We won't mess with that right now. But let's reevaluate 2, 4, 6, 8. 2, 4, 6, 8. Since the bonded electrons count for both, octet rule is satisfied. Subtract 12 for the electrons, and we don't have anything left. We satisfied the octet rule. We're peachy, right? Now on oxygen, you're going to get 2 times oxygen's in group 6, so 6 is 12. So we're going to have a bond and a bond. So that's going to take away 2 electrons for a total of 10. But when I try to evaluate my octet rule, each oxygen is considered to have 2, so it would need 6 to get to 8. 6 times 2 is 12, and I don't have that many electrons. This is where the double and the triple bonds come in. So since I'm 2 electrons short, that implies I need to add a double bond. So that takes away 2 more and leaves me with 8. Now, if we evaluate the octet rule again and see if that helps us, each oxygen is considered to have 4, so they would need 4 more for a total of 8. And once you get to what you need is what you have, you can just finish it out with the non-bonding electrons. So I'll take away 8 and leave me with none. Now for nitrogen, there's 2 of those. And nitrogen is in group 5. So 2 times 5 is 10. So I'm even 2 worse than I was in this case. So if I take away 2, that's going to put me at 8. Except now I still need 12 electrons to finish that out, but I've only got 8. I'm 4 short. That would imply more than 1 double bond or 1 triple bond. In this case, there's only 1 place to put bond, so it has to be a triple. So each line represents a bond. So that would be a triple bond. This would be a double bond. But when I add in 4 more and I take that away from my total, I got 4 left. Now each nitrogen only needs 2, so we're just going to stick those on there now. I don't have any left, but that is a proper structure that obeys the octet rule. Next, we're going to work some Lewis structure problems with compounds, and we'll see how they are different. And the bottom two do carry a net charge, and so we'll get to factor that in. Right, now that we're getting the hang of it, let's draw Lewis structures for water, ammonia, CO2, and then we'll hit the charged ones next. So now I've got to add in more than one element. So I've got hydrogen and oxygen to add in. I've got 2 hydrogens times 1 valence electron, because it's in 1A, is 2. Oxygen, there's 1 oxygen times 6 valence electrons, because it's in 6A, or 6, for a total of 8. Can I get all 8 electrons on the structure? Let's find out. Now I'm not drawing this to illustrating sort of geometry. We'll talk about that later. There's a single bond connecting hydrogen to the oxygen. Now, the types of bonds that we're going to draw are ones usually where there's one central atom that is an atom in the middle, and then outer atoms called substituents. And so the one there's only one of, or the biggest element, is usually the one in the middle. If I take away 4, that's going to leave me with 4 left. Where do those 4 electrons go? They have to be non-bonding pairs on the oxygen to fill out the octet rule. Ammonia, nitrogen, hydrogen. 1 times 5 is 5. 3 times 1 is 3. That's going to give me 8, just like in this case, except now there are 3 bonds between nitrogen and hydrogen. That's going to be 6. It's going to leave me with 2. Where do those 2 electrons go? On the nitrogen. So carbon dioxide now, got carbon, it's got oxygen. 1 carbon, carbon's in group 4, so 1 times 4 is 4. There's 2 oxygens times 6 for a total of 12. That's going to give me 16. So if we do carbon, single bond to oxygen, single bond to oxygen, that'll take away 4. That's going to leave me with 12. Problem comes up, need 6 there, need 6 there. That's 12 already. But then the carbon needs 4 to get to 8, because that's where I got the 2 bonds. So I need 16, but I only have 12. That's going to imply one double bond, more than one double bond, or a triple bond. As you might imagine, double bonds are more symmetric. The experimental data shows that it's got 2 carbon-carbon double bonds, because usually a single bond is long, a double bond is shorter, triple bond is shorter still, and these are more consistent with the carbon-oxygen double bonds in this particular molecule. But doubling the bonds will take away 4, and that'll leave me with 8. Carbon's octet is happy. Each oxygen still needs 4. 4 times 2 is 8. So we stick it on there. And that's a proper structure for CO2. Now, I said you could technically draw a structure that obeyed the octet rule that had a triple bond in it. And it would look something like this. But this would imply a asymmetric molecule, and that's not what really occurs. This is not considered a good structure, even though it technically obeys the octet rule. When we talk about formal charge, I'll explain why that's not a good structure, perhaps in a little bit more detail. Now, this is one that carries a net charge, so we're going to have to account for that. So we've got nitrogen, we got oxygen. 1 times 5 for nitrogen is 5. 3 times 6 for oxygen, because those are the number of valence electrons, is 18. That would give me 23. That would give me an odd number of electrons. You want to be careful of that. If you legitimately end up with an odd number of electrons, that's something called a free radical, which doesn't come up that often at this level. But in our case, we haven't accounted for that -1 charge yet. We're going to add 1, and that's going to give us 24. Let's draw our structure then. Bonds to nitrogen, that's going to take away 6, leave us with 18. Each oxygen needs 6. 6 times 3 is 18. but the nitrogen still needs 2, so that would be 20. So I need 1 double bond. Doesn't matter where I put it. So then 12 plus 4 is 16. Those two are nitrogen's happy. This one's a little different, but then I'm going to fill in the octets with non-bonding electrons. Then you say, well, I arbitrarily put one here. Turns out you could have drawn that double bond in any of a number of different locations. And you could draw 3 different equivalent structures just by moving the double bond around. And that's okay. In this case, all these are equally correct, unlike the CO2 case. Now, technically, they all carry a -1 charge, so a lot of times people put brackets around them and indicate the charge outside, because it's the whole molecule that's charged, not just a particular atom. And so any of these structures are interchangeable. And we end up calling those resonance structures. Last but certainly not least, we have our friend the ammonium ion to give us one that's positive. So we're going to have nitrogen. 1 times 5 is 5. Hydrogen, there's 4 of those, times 1 is 4. That's going to give us 9, but we're going to subtract 1 for the positive charge, which will give us 8. And so I draw 4 covalent bonds to nitrogen to hydrogen. That's 8 electrons, so it just works out nicely that way. And that would be a completed Lewis structure for the nitrogen. Again, we're not showing geometry on any of these structures.